Okay, let's unpack this. Welcome back to the deep dive. Today we are opening up a strategic blueprint that really it defines the next 2 decades of transportation.
It really does.
We're looking beyond the battery, beyond the chassis, and straight into the ultimate control point, the software brain of the intelligent connected vehicle.
And the strategic importance here, I mean, it just can't be overstated. The car is no longer just a way to get from A to B.
Not at all.
It's becoming the ultimate carrier for this whole new tech revolution.
Yeah.
We're talking AI, sophisticated cloud infrastructure, massive big data processing.
But what is its central intelligence? I mean, what's its soul? It's the vehicle operating system, the VOS.
Precisely. And for this deep dive, we're pulling directly from a really high-level professional analytical report. It's basically a technology roadmap written in a consultancy style.
Right.
And this report treats the VOS not just as some subsystem, but as the core platform that's going to dictate all future innovation. And, maybe more importantly, define industrial sovereignty.
So our mission today is, well, it's ambitious. We're going to extract that strategic vision, that big, grand 2040 goal, and then we're going to trace the tiny, granular, quantifiable technical milestones.
The ones set for 2030, 2035, and 2040.
Exactly. And that's the difference, isn't it, between a philosophical chat and a detailed engineering plan.
And you can already see this vision shaping what big companies are doing globally. I mean, look at Mercedes-Benz. They're pushing so hard with their own proprietary MBOS.
That was all over CES this year.
It was. And they're drawing a really firm line in the sand. They're basically saying we want total control over the customer experience and the data pipeline.
And it's not just the car makers, right? The suppliers are morphing into software giants.
Oh, completely. You're watching these traditional hardware powerhouses like Bosch and Continental. They're elevating their specialized software subsidiaries, ENS and EB, into core strategic divisions.
That's a huge internal shift.
It's massive. It's a recognition that the value is migrating from sheet metal to lines of code.
Then you have these critical tech partnerships that are forming the new backbone of the industry.
You mean like NVIDIA teaming up with BlackBerry QNX?
Exactly that. That alliance isn't an accident. It creates that crucial OS plus high-performance chip plus toolchain ecosystem.
And it's completely dominating the high-end autonomous driving stack. This is the competitive landscape that you, the listener, really need to grasp.
So if the stakes are this high, what is the core value proposition of controlling the VOS? I mean, why is this software foundation worth literally trillions in investment and strategic effort?
Well, the strategic analysis we're looking at, it breaks the core value down into four non-negotiable pillars. The first, and it's the most obvious one, is that the VOS enables intelligent connected scenarios.
Okay.
It has to be robust enough, responsive enough to support petabytes of data, run these huge AI models, handle complex driving algorithms, and manage, high-level multimodal user interaction.
So without the VOS as a solid foundation, none of the fancy features actually work.
They just don't.
Yeah.
That's the functional requirement. The second pillar is, well, it's existential. Securing national information and industrial safety.
Right, this is the sovereignty piece.
Exactly. The VOS is the definitive platform for the software-defined vehicle. If your core software, the kernel, the hypervisor, the middleware, is foreign, proprietary, a black box,
Then you have a fundamental strategic vulnerability.
a huge one for data privacy, for national security, and for industrial autonomy. So control of the VOS is industrial sovereignty.
That framing makes it so clear why this is a strategic national focus, not just a commercial one. What about, actual physical safety on the road?
That's the third pillar. The VOS has to demonstrably enhance vehicle and traffic safety, and this translates directly into engineering requirements.
Like what?
Incredibly low latency, super high response speeds, and real-time V2X communication vehicle to everything. It needs to guarantee quick, accurate reactions in these extremely complex dynamic traffic situations.
Which then feeds into that larger vision of smart cities and smart transportation.
Precisely. And the final piece of the puzzle is how this software foundation helps build an entire industry.
Right, the ecosystem.
The fourth pillar is crucial: fostering an open innovation ecosystem. The VOS, through an open source or at least an open architecture model, aims to fundamentally decouple the algorithm and application layers from the proprietary hardware below.
So from the chips, which are often foreign-made.
Exactly. This breaks that dependency, it accelerates the development cycle, and it fosters this broad collaborative development across the entire supply chain. And that's essential for long-term sustainability and reaching critical mass.
Okay, let's unpack this. Before we get into the truly audacious goals for 2040 and those insane microsecond metrics, we have to understand the current competitive reality. Where do things stand today? And specifically, where are the critical gaps that domestic efforts have to fill to even compete with these international giants?
Well, the VOS landscape today is really defined by functional separation. It's largely driven by safety requirements.
Oh, it's not all one big system.
Not yet. It splits into two main areas. You have the car control OS, which handles all the safety-critical functions and intelligent driving execution, and then you have the in-vehicle infotainment OS, or IFE.
The I being the part that manages the cockpit experience, the screens, the audio, all the non-critical apps.
Exactly. And in most cars on the road today, they're run on separate hardware, or at best, they're in these strictly siloed virtual environments.
Let's focus on the safety and driving side first, the car control OS. The report highlights two dominant and quite different technical routes being chased internationally for the intelligent driving OS.
That's right. The first route, which represents a truly centralized holistic control philosophy, is deep Linux customization.
And Tesla is the poster child for this.
Absolutely. They essentially built a single, highly tailored OS based on Linux that manages everything, from the low-level driving functions and high-level navigation to the complex battery management and thermal control.
So that gives them this unified control. It minimizes communication friction between domains because it's all running under one big umbrella. It's monolithic, but it's incredibly customized.
It is. It achieves that centralized control, and it really simplifies the software update cycle. You also see Red Hat's work in the in-vehicle OS space following this philosophy.
Yeah.
Leveraging open source Linux, but customizing it deeply for deterministic automotive use.
The big challenge there must be proving functional safety, getting that ASIL certification across such a huge, complex code base.
That's the main hurdle, which brings us to the second major route.
Which is?
The more established layered approach is built around safety partitioning. This combines a safety RTOS, a real-time operating system that's optimized for deterministic speed, with AUTOSAR AP, the adaptive platform for application services.
And the gold standard here is NVIDIA Drive OS.
It is. It uses BlackBerry QNX for the safety-critical real-time functions. It integrates Linux for flexibility and advanced processing. And then it uses AUTOSAR AP for standardized inter-system communication, the middleware.
So instead of one massive custom system, this is modular. The safety-critical parts are isolated in a guaranteed real-time environment, while the complex AI models run on the more flexible Linux side.
Right.
It sounds inherently safer, but maybe a bit slower to communicate between the parts.
That's the trade-off. It provides amazing graphical processing, and it's ideal for running deep learning algorithms while maintaining that robust isolation, which is just crucial for safety certification.
Okay, so when we look at domestic players, the report suggests they're aiming straight for fusion architectures. They're trying to leapfrog these separate approaches. Why the big rush to merge?
The urgency comes from efficiency and the need to catch up on features really quickly. Running separate domain controllers is expensive, and it limits how you can share data.
Right.
So by pushing fusion architectures, they're trying to leverage a single, powerful central computing platform. You see this with Huawei's AOS, which is built on the microkernel structure of HarmonyOS, running on their own MDC hardware platform.
So they're trying to leverage a known microkernel, which is inherently designed for security and compartmentalization, to build an entire OS from the ground up.
That's the idea. And then you have ZTE, which is using more of a hybrid strategy.
Mixing and matching.
A bit, yeah. A traditional safety Linux for the higher functions combined with their own self-developed microkernel solution. That's a common strategy. You use Linux compatibility to tap into the app ecosystem developers already know,
while you isolate the most time-critical or security-sensitive functions on your custom microkernel.
You've got it.
I think the Zebra Zixing Alios drive architecture is really fascinating. They use a dual-core approach that's fused by a hypervisor. Can you expand on the strategy behind that?
Absolutely. The Zebra Zixing architecture uses their microkernel, Alios RTOS, for the extreme real-time tasks, and then Alios Safety Linux for the more complex but less time-critical functions. The key piece, as you said, is the hypervisor.
So the hypervisor is like a virtual traffic cop.
A perfect way to put it. It's a virtual layer that lets these two totally distinct operating systems share the same physical hardware, the CPU, GPU, memory, without ever interfering with each other.
So it's an explicit attempt to get the real-time security of an RTOS while keeping the huge app ecosystem and flexibility of Linux all managed under one unified roof.
That is the strategic intent.
Okay, let's pivot to the cockpit and IVI systems, the user-facing side.
IVI systems are generally custom versions of established OCs, QNX, Linux, Android, or HarmonyOS. And here, using a hypervisor to run dual systems is pretty standard practice.
For instance.
You might run QNX for the critical non-negotiable dashboard gauges.
Yeah.
Your speedometer, your warning lights, things that have to be functionally safe and instantaneous. And at the same time, you run a feature-rich system like Android for the central console entertainment and navigation.
So the hypervisor partitions the resources, guaranteeing that if Spotify crashes on the entertainment system, it doesn't freeze your speedometer, which would be a major safety hazard.
Precisely. BlackBerry, Huawei, and Zebra Zixing are the core domestic players in this IVI space. But this brings us to the core issue identified in the strategic analysis, this high gap in the system software layer.
The invisible foundational software below the application level.
And it's the biggest dependency bottleneck.
Let's break down that gap across the three crucial system components. Start with the kernel.
The kernel is the deep core of the OS, the master controller of the hardware. And internationally, players like QNX, Linux, and Android just dominate, not just in market share, but in maturity, application breadth, and the robustness of their ecosystems.
Right, a kernel takes decades and millions of lines of code to fully mature and address every weird, obscure corner case.
So while domestic products exist, and they are functional, they just haven't had the decades of battle testing across thousands of different hardware configurations and extreme operational environments that something like QNX or Linux has.
That's the critical vulnerability. They lag significantly in maturity and widespread application. When a bug pops up, it affects millions of vehicles globally, but that also means millions of data points are used to fix it.
And the domestic efforts just haven't reached that scale, which translates directly to higher risk and much slower development cycles.
Okay, the second gap is in virtualization technology, that hypervisor layer we just talked about.
Foreign systems have a massive accumulated advantage here, particularly in functional richness, sophisticated I/O virtualization, which is crucial for efficiently sharing peripherals like cameras and sensors, and robust tool support.
Building a hypervisor that can reliably manage ASIL-D safety requirements while giving you near-native performance has to be exceptionally complex.
It is. And domestically, while the report says they're catching up rapidly, companies like Zongling Zixing and Zebra Zixing are closing the technical gap and have achieved scale verification. The critical issue is they lack international application scale. They haven't been tested across the global ecosystem, which means their tool chains and compatibility frameworks are just less mature.
It's the difference between testing in a lab and launching worldwide. Finally, the gap in middleware.
Middleware is what facilitates standardized communication. International standards like AUTOSAR are incredibly well established. They provide a common language so components from different suppliers can talk to each other reliably.
And domestically, progress is good, but there are shortfalls.
The shortfall is particularly acute in the safety control middleware, which is complex and requires specialized certification, and intelligent driving middleware, which is still kind of nascent. It's struggling to standardize communication between this explosion of new sensor types and AI models.
So the reliance on foreign standards makes it hard to innovate without conforming to someone else's rules.
Exactly. The required strengthening of toolchain support is a huge engineering hurdle.
So the core takeaway from this current battlefield analysis is clear. Global leaders control the foundational black box of system software. If you don't control the kernel, the hypervisor, and the communication standards, you are fundamentally dependent on someone else's tech.
And you're constrained by their pace of innovation.
Now let's transition to the future. How does this roadmap, which looks all the way out to 2040, propose to break through this reliance and achieve genuine, self-controlled global leadership?
The 2040 vision laid out in this report isn't just about a better piece of software. It's about redefining the vehicle's place in society. The VOS has to become the vehicle's control hub and intelligent brain.
Its purpose is to be the connecting bridge.
Exactly. Linking the vehicle to the entire outside world, supporting smart transportation, optimizing efficiency, and contributing to low-carbon development.
It sounds like moving from a product focus to a systems focus. So let's revisit those four pillars as future capabilities. What does intelligence look like by 2040?
Intelligence means native AI integration. We are talking about supporting L5 fully autonomous driving, which is complete, unsupervised automation in all conditions, and at the same time, running L4 comprehensive cognitive smart cockpits.
So the OS itself has to be natively capable of AI processing, decision-making, and self-learning.
It does. And for interconnection, full V2X support means seamless, high-bandwidth integration with everything.
Not just other cars.
Not just other cars. Traffic lights, road sensors, city management systems, and crucially, smart homes. The car shouldn't just drive you home. It should be coordinating with your home automation system, your energy grid, and the nearest delivery drone.
And security. We already touched on the split between functional safety and network security. How does the 2040 vision fuse those?
Security has to evolve into this complex integrated synergy. It has to be functional safety plus network security plus data security. The goal is a unified, multi-level safety guarantee system that's managed by the OS itself.
And finally, that ecosystem goal achieving that internationally oriented open source platform.
This is maybe the most strategic goal of all.
Right.
The VOS has to attract global developers by being truly open and competitive, breaking down the existing foreign proprietary standards and establishing a new, robust standard that other people choose to adopt.
So to realize this huge vision, the roadmap maps out the VOS evolution in 3 phases, and it directly traces the industry's shift from fragmented domain controllers to a powerful central computing concept driven by service-oriented architecture, or SOA.
Right. The first big step is 2030, the preliminary fusion phase. The core technical goal is integrating the car control OS and the IVI OS onto a single, powerful platform.
So the cockpit and intelligent driving functions start to seamlessly merge?
They merge into one interactive experience, achieving cross-domain sharing of functions and critical sensor data.
And the safety baseline for 2030 it's terrifyingly high?
It is. The stability target is explicitly defined as 0 breakdowns caused by the VOS. 0. For a mass-produced, safety-critical software stack controlling a vehicle at highway speeds, that is the ultimate engineering hurdle. It means anticipating and mitigating every possible software failure mode before it happens.
Wow. That sets the stage for 2035, the phase fusion year.
This is the transitional core. The main goal here is forming a vehicle road cloud coordinated fusion intelligent self-adaptive VOS. Let's just call it the integrated VOS.
Good idea.
The central computing platform is fully established, fusing car control, intelligent driving, and IVI functionality seamlessly. An initial self-adaptive capability is realized.
Meaning the OS can dynamically adjust resources and manage complexity on its own?
Exactly. And the strategic commercial goal is to establish one internationally renowned VOS brand.
So that 2035 target is the moment of international market entry and validation, which brings us to the final step, 2040, fusion intelligence.
This is the full vision realized. The integrated VOS deeply merges with cloud services, moving intelligence between the edge, the car, and the cloud. It supports total vehicle intelligence and seamless interconnection.
And by 2040, the goal is market maturity, establishing 1 or 2 internationally renowned VOS brands.
Supported by a globally thriving, vibrant ecosystem, competitive not just in tech, but also in cost.
Now, you mentioned this whole evolution is mandatory because the industry is shifting to a service-oriented architecture, or SOA. For the listener, why is this architectural shift absolutely mandatory to hit those 2040 goals?
Think about the traditional EE architecture, the old way cars were built, with dozens of separate electronic control units, or ECUs. It's fragmented.
Right. Hardware and software are deeply coupled. So if you change one piece of hardware, you have to rewrite the software for that specific box.
And that leads to insufficient compute power in any one place, bandwidth bottlenecks between all those separate boxes, and it makes over-the-air software upgrades incredibly difficult.
It's like trying to manage an office where every employee has their own separate, non-networked mini computer for just one task. It's inefficient and impossible to upgrade.
That's a perfect analogy. And SOA addresses this. The future demands a centralized, layered, decoupled, and unified interface architecture. The integrated VOS, built on SOA principles, treats all vehicle functions as services that can be called up centrally, no matter which physical chip they're running on.
Which allows for centralized resource scheduling, dynamic configuration, and it must radically accelerate the speed at which you can deploy new features.
And monetize them.
That vision is profoundly ambitious. To get to 0 breakdowns, L5 autonomy, and seamless fusion, we need precision. Now, let's drill down into the hard, quantifiable metrics. We're moving from high-level vision to pure engineering rigor, starting at the atomic level of the software, the kernel.
This is where the rubber really meets the road. In a consultancy-style roadmap, these quantifiable targets are the substance. They translate that grand vision into precise, non-negotiable engineering tasks.
And for you, the learner, these performance metrics define the demanding, unforgiving, real-time needs of L5 autonomous driving.
So let's start at the foundation. Kernel technology. This governs real-time precision and is the ultimate measure of reliability and safety.
The entire vehicle's stability depends on these speeds.
And the requirements for latency, the delay between a command and the hardware responding, are just staggering. We're tracking interrupt response times. For 2030, the roadmap aims for the intelligent driving interrupt response delay to be less than 10 microseconds. That's 10 sunnies.
Okay, to put 10 microseconds in the context, that's 10 millionths of a second. In that time, light travels about 3 meters, so the software has to react faster than almost any human reflex.
It does. And the safety control response delay has to be even faster, less than 5 microseconds. System startup has to be under 2 seconds, and the OS needs to adapt to over 50% of the SoC chips on the market.
By 2035, these goals tighten. They're literally shaving off half the time.
The intelligent driving interrupt response delay must be reduced to less than 5 microseconds. System startup drops to less than 1 second. And the engineering effort required to safely and reliably shave off those few microseconds across a growing code base is just immense.
And the ultimate target for 2040 reveals the true precision needed for safety-critical L5 autonomy.
The safety control interrupt response delay is reduced further to a blistering less than 2 microseconds, 2 senches.
Wow.
This level of speed guarantees the vehicle's control loop is tight enough to handle high-speed corrections. If a sensor detects an imminent crash, the kernel has to execute the safety response in less than 2 millionths of a second. This is the definition of ASIL-D reliability.
And this 2040 goal also defines the requirement for the integrated VOS, for the fusion.
It does. The critical goal for kernel fusion is that the cross-kernel remote process communication delay must be within 5% of local process communication.
What does that mean in practical terms?
It means if your car control and IVI are running on different kernels, they have to communicate almost instantaneously, as if they were running on the exact same piece of software for real-time safety functions to coordinate. Achieving that 5% parity requires a revolution in inter-process communication protocols.
Okay, moving up a layer to virtualization technology, the hypervisor. This is how they achieve safety separation and max efficiency on centralized hardware. What are the metrics for success here?
For 2030, focusing on single machine virtualization, the goal is efficient resource use with minimal overhead. Performance loss for the critical components, CPU, GPU, and NPU, must be less than 5%.
That seems like a reasonable trade-off. You get the safety of virtualization for a tiny 5% performance hit.
But, and this is the crucial part, this entire stack must simultaneously pass the highest automotive functional safety certification, ISO 262622 ASIL-D.
So the hypervisor itself has to be proven to be incredibly reliable.
Exactly. Achieving high performance and ASIL-D compliance at 5% loss is a monstrous engineering task.
By 2035, the goal shifts to what they call ecological virtualization.
Right. VOS penetration is targeted to reach 80%. It becomes the industry standard. And performance loss is optimized even further. CPU, GPU, and NPU loss has to drop to less than 3%. The virtual layer becomes practically invisible to the application.
Which is required for complex AI models that just can't afford any performance degradation.
Exactly. And by 2040, the system becomes fully distributed.
A distributed virtualization system.
Right. Integrate the edge, the car, and the cloud. The goal here is radical. Distributed virtualization performance should be infinitely close to native performance. The loss should be negligible. The key challenge becomes smart resource management. The OS has to intelligently predict and analyze real-time usage to dynamically allocate resources across the whole system.
Incredible. Next, the layer that links all these complex components, middleware technology, the communication fabric.
In 2030, the focus is stability. Response time has to be controlled at the millisecond level, and reliability measured by mean time between failures, or MTBF, must exceed 100,000 hours.
100,000 hours MTBF. That's roughly 11.4 years of continuous, non-stop operation. That's the baseline for reliability.
By 2035, the targets accelerate dramatically. Response time gets compressed from milliseconds down to the microsecond level.
So 1,000 times faster.
1,000 times faster. And MTBF increases 5-fold to over 500,000 hours. This is also the point where the middleware starts to incorporate native AI for intelligent maintenance and fault prediction. It can predict when a component might fail before it impacts safety.
So not just fast and reliable, but self-aware and self-diagnosing.
Exactly. And by 2040, middleware achieves full intelligence. It has to autonomously analyze data streams, predict bottlenecks, and optimize resource allocation. The roadmap even specifies incorporating frontier communication tech like quantum communication,
Which is future-proofing for the insane data pipes needed for L5 autonomy and complete vehicle road cloud sync.
You've got it.
The sheer magnitude of these performance jumps, from 10 signs to 2 signs latency at the kernel, the shift to microsecond middleware response. It confirms this is a pure, high-precision engineering plan. It's what's required to move from driver assistance to full, robust L5 autonomy.
It is.
So let's look at how the application and connectivity layers have to evolve to exploit this hyper-fast foundation.
As the foundational OS layers achieve that hyperspeed and certification, the application layers, the parts that actually drive the car and interact with the user, they have to achieve the necessary performance to realize L5.
Let's talk about car control function software, specifically for L3 Plus through L5 driving systems. What are the key performance indicators here?
It's all about end-to-end performance certainty, from the moment a sensor detects something to the moment the wheel turns. For 2030, the system must support L3 Plus intelligent driving and integrate end-to-end AI large models, specifically mentioning architectures like BEV plus transformer.
Okay, let's unpack BEV plus transformer really quickly for the listener.
So the bird's eye view, or BEV plus transformer model, is an advanced sensor fusion architecture. Instead of processing 12 separate camera feeds individually, it fuses all the sensor data cameras, LiDAR, radar, into a single unified 3D map of the environment.
The bird's eye view.
Exactly. The transformer models, which are borrowed from large language models, then interpret that unified map to predict where every object is going and make control decisions. It's what enables robust, complex decision-making.
Got it. So what are the latency requirements for this complex end-to-end system?
The deterministic latency for scheduling needs to be less than 100 microseconds, but the full end-to-end latency from sensor input through all that processing to actuator output must be less than 35 milliseconds.
And 35 milliseconds is roughly the physiological limit of human visual and reaction time. So the car has to process the world and react faster than a human driver to be inherently safer.
And by 2040, that threshold is pushed to the absolute limit. End-to-end latency drops to a blisteringly fast, less than 12 milliseconds to nanometers. This reduction is crucial for high-speed, dynamic L5 scenarios. Furthermore, the fault recovery time, how fast the system can isolate a failure and stabilize, has to drop from 50 milliseconds in 2030 to less than 10 milliseconds, 10 meters. This is recovery speed essential for guaranteeing ASIL D compliance.
Okay, now for the raw horsepower. Let's talk about the true AI brain, the Intelligent Technology Roadmap. We're looking at TFLOPS requirements, a measure of compute performance.
We see 3 sharp, quantifiable jumps. In 2030, the requirement is 100 TFLOPS. That's already significant power.
And by 2035?
That jumps 5-fold to 500 TFLOPS. This jump is necessary to support high-level intelligent reasoning, so not just seeing what's there, but understanding intent and context.
And the 2040 target, that number looks astronomical.
2040 demands a staggering 2,000 TFLOPS, 2 petaflops. To give you some context, that's roughly the compute power of some of the world's most powerful research supercomputers from about a decade ago.
But miniaturized, ruggedized, and optimized to fit inside a car and run off a battery.
Exactly. This colossal performance is needed to support full intelligence. Running multiple redundant L5 models, high-def mapping, real-time cloud data integration, and enabling genuine self-evolution and continuous learning.
So what does a 2040 intelligent vehicle actually do with all that power?
By 2040, the system must achieve L5 fully autonomous driving and operate an L4 cognitive smart cockpit. The features are futuristic. The sources specifically mention the VOS needing to support advanced interfaces like holographic projection.
Holographic projection.
And the integration of brain-computer interfaces for highly personalized control. Functionally, it has to provide fully automated predictive services for travel, entertainment, and even health management, turning the vehicle into a true autonomous mobile living space.
That level of connectivity and control demands a completely transformed security technology roadmap. We're moving from protecting a car to protecting a mobile supercomputer.
We are. Security has to transition from a segmented, reactive approach to an integrated, resilient one. The target is to evolve from separate functional safety and network security regimes to the unified synergy of functional safety plus network security plus data security.
And what's the ultimate security goal for 2040?
The VOS must possess self-adaptive and self-growing resilient defense capability. It needs to be tough enough not just to detect known attacks, but to learn, adapt its defenses, and recover quickly. The most demanding technical hurdle is in threat detection itself.
Explain that jump in detection capability.
Well, today most security systems rely on characteristic knowledge bases. They have a library of signatures for viruses and attacks. The 2030 goal is about improving this.
Mm.
But the 2040 roadmap sets the goal to move to detection that is fully independent of characteristic knowledge bases.
Ye-
It means the security layer, driven by AI, has to be able to identify a threat as it's happening, without ever having seen that specific attack signature before. It requires pushing AI deep into the security layer to enable true anomaly detection and zero-day defense against unknown threats.
That's a massive paradigm shift in computer security, from signatures to predictive behavior analysis.
It's the ultimate goal of security engineering. And finally, underpinning all this is connectivity. The interconnection roadmap dictates basic realization of low latency, high reliability, and cloud integrated communication by 2030. Think robust 5G and edge processing.
And the 2040 ambition for connectivity.
Full integration of advanced communication, again citing the potential of quantum communication, to provide seamless, ultra-low latency connectivity for that full vehicle road-cloud synergy. The network capacity has to reliably support the 2000 TFLOPS AI brain and the petabytes of data it's continuously generating.
This roadmap is astonishing in its quantitative rigor. It lays out a precise engineering path for every layer of the OS stack. Now we have to address the final crucial component. The governance, standardization, and commercial strategy needed to actually implement this plan and achieve global standing.
And all these technical targets, the 2000 latency, the 2000 TFLOPS, they are fundamentally driven by one strategic imperative: self-reliance. The analysis strongly emphasizes the national strategic urgency to develop robust domestic alternatives.
And that's driven by the critical vulnerability of relying on proprietary foreign tech like Linux, Android, and QNX, which define the current global market.
Exactly. This circles back to the guiding mandate: to win the critical battle for the domestication of operating systems and foundational software.
Right.
The dependence on foreign standards leads to two primary problems. First, it constrains innovation. Second, it causes fragmentation and this fierce internal competitive exhaustion among domestic firms, all chasing slightly different, incompatible technical routes.
So the VOS is seen as the catalyst that will unify efforts, break the foreign chip and algorithm dependency, and channel resources into a single collaborative ecosystem.
That's the plan.
To break that dependency, they need to control the entire development lifecycle. Let's look at the roadmap for standards, testing, and tool chains. This is the sovereignty check.
This is the shift from being an international follower to an international leader and standard setter.
Yeah.
The rigor of testing is relentless. Test coverage rate targets are 90% by 2030, 95% by 2035, and an unprecedented 99% by 2040.
99% test coverage for software is nearly impossible to achieve, particularly in a high-complexity, safety-critical environment. It signals an extreme commitment to verifiable infallibility.
It does. But the most ambitious goal for sovereignty lies in the autonomous controllable tool target. The goal is total independence over the software creation pipeline itself.
So building an entire autonomous toolchain compilation, integration, testing, simulation, deployment that is fully controlled domestically.
And removes all external dependencies.
This is about digital supply chain security. If you control the compiler, you control the final code. What are the metrics for this control?
Toolchain coverage has to reach 80% by 2030, 90% by 2035, and achieve 100% autonomous control by 2040. This means total independence from reliance on external software development kits, proprietary OMEZs for development, and foreign simulation environments.
And the toolchains themselves have to be cloud-native and intelligent.
And heavily supported by AI to optimize development and verification speed, ensuring superior functionality, not just control.
Let's discuss the commercial goals, the market and ecosystem targets. How do they translate this massive technical effort into commercial success?
By 2030, the critical milestone is scaled verification domestically. The system software and core technologies have to be fully proven and deployed in real-world application across a significant volume of vehicles.
By 2035, they move from verification to market dominance.
The domestic market share goal is to exceed 50%, coupled with the formation of that first internationally renowned VOS brand. This is the inflection point where the domestic alternative becomes the default standard.
And the final commercial goal for 2040?
Development of one or two internationally renowned VOS brands, achieving strong international competitiveness, not just on technology, but crucially through pricing advantages.
Which signals that the entire localized ecosystem, chips, OS, toolchains, has reached a level of scale and efficiency to compete globally on cost.
And become an attractive platform for international OEMs.
And the mechanism for achieving consensus and sustaining development? Open source.
Yes.
Yeah.
The roadmap clearly mandates the use of an iteratively updated open source baseline. This strategy is essential to focus core technology development, build consensus among competing domestic firms, and accelerate the ecosystem development by making the base platform accessible and collaborative.
So open source is the strategic lubricant designed to overcome internal fragmentation.
That's a good way to put it.
So the entire roadmap is a marathon defined by this high-stakes shift, from segmented, localized systems built on foreign foundations to a unified, intelligent brain that is entirely self-controlled, self-adapting, and links seamlessly with the world, establishing a new global standard.
That's the vision in a nutshell.
What stands out to me in this deep dive is the breathtaking level of quantitative detail. This consultancy-style roadmap isn't just a political aspiration, it is a comprehensive engineering manifesto.
It really is.
It specifies 2 microsecond latency targets, 99% test coverage, and 2,000 TFLOPS of compute power. It forces us to view the future of the car not as a vehicle, but as a high-precision, safety-critical mobile data center.
And if we connect this to the bigger picture, I think the ultimate determinant of success in achieving this vision is not merely hitting those staggering technical targets. The 2000 TFLOPS and the 2 microsecond latency, those are solvable engineering problems with enough resources.
So what's the real challenge?
The core challenge is successfully migrating the ecosystem,
Why is the ecosystem migration the biggest hurdle?
because it means transitioning the entire industry, suppliers, chip makers, application developers, OEMs, from heavy reliance on decades of established foreign platforms like QNX and Android and their mature, battle-tested tool chains to adopting a new, robust, and internationally compatible standard.
Technology is built by dedicated teams. Ecosystems have to be built by the world.
Exactly. And attracting that global talent and investment requires proving not just technological parity, but long-term sustainability and neutrality.
For you, the learner, this roadmap illustrates the fierce, high-stakes competition defining the next generation of transportation. The vehicle is becoming the most valuable computing node outside of the data center, and whoever owns the operating system owns the customer experience, the data pipeline, the safety standards, and ultimately, the future profits and control of the entire mobility sector.
And this raises a really important question for us all to consider. Given the incredibly tight real-time performance and absolute safety requirements, specifically ASIL-D certification, and that demanding less than 2 microsecond latency demanded of the VOS kernel in the 2040 vision,
Right.
can an open source model, by its very nature, truly compete against highly optimized proprietary commercial kernels in the high-stakes, safety-critical domain of L5 autonomy? Or will some form of controlled, closed-source optimization always win the race for ultimate, verifiable reliability?
A fascinating tension between openness and control right at the critical safety layer, something to mull over as you watch this high-speed, high-stakes landscape evolve over the next 2 decades. Thanks for diving deep with us.
My pleasure.
We'll see you next time.